Today we're going to be talking about radicals and rational exponents. So first, let's knock out some vocabulary here just so that we all know what we're talking about. If you remember, a radical is a symbol, specifically this symbol. This is a radical. And we generally use this symbol, so far you've used it mostly when you've been discussing square roots. And if you remember, a square root is the opposite of squaring something. So for example, 2 squared would be 2 times 2, which equals 4. So the square root of 4 is saying what times itself is equal to 4, so the square root of 4 is 2. Those were opposites of each other, and so this has generally been the use of the radical form that you have done up to this point. What you do need to realize is that it is not called the square root symbol. You may have heard it referred to that before, but that's not actually its name. It is called a radical, and it can be used for things other than just square roots. In fact, it's used for all of our roots. There are other roots other than just the square root, because we can square numbers, but we can also do other powers of numbers. All of the powers have an opposite root. So for example, 2 cubed would be 2 times 2 times 2. 2 times itself 3 times, which is equal to 8. So there has to be an opposite of that, and the opposite of cubing something is the cube root. So how would we write a cube root? So the radical implies that it's a root, so that's the symbol. So I could do this, but this would be the square root of 8. When you do not write a number there, then it is assumed to be the square root. But if there is a little number, it's tiny, and it sits on that shelf, this tells us which root we are dealing with. So by having a 3 here, just like we had a 3 in the exponent over here, this tells us that this is a cube root, or the third root. We do have a name for this number. This number here is called the index. So there's another vocabulary word for you. So this is our index. This is the radical. The number that's inside is called the radicand. Okay, so the number underneath the radical is the radicand. We have the radical, the symbol itself, and the little number that sits on the shelf is called the index. In case you have forgotten, this number up here is called an exponent. Okay, so we have some vocabulary. I do want to point out again, if there is no number written on the shelf of the radical, then that is an understood. It's an understood 2. If they don't tell you what the index is, then you assume that the index is 2, a square root. It's the most common. And again, mathematicians, being lazy, want to write as little as possible. So since we use the square root the most often, we just went ahead and said, okay, so if there's not a number written up there, it's a square root. If it's got to be something different, then we'll write it up there. But just assume that if there's not a number written up there, it's a square root. So that's where that came from. So we have our radical, we have our index, we have our radicand. The important thing to remember about these roots is that they are the opposite of that power. So we reduce these radicals very much in the same way that we reduced square roots. If you remember, if I have something like the square root of 8, we said, well, 8 isn't a perfect square. It doesn't have a square root. So we would have to figure out, well, is there a perfect square? So we would think about all the numbers that are squared. So 2 squared is equal to 4, and 3 squared is equal to 9. Well, that's already too big. But I'm like, oh, but 4 will divide 8. So we take and we say, okay, well, 8 is 4 times 2. And then when we take the square roots of those individually, the square root of 4 is 2. And this just stays the square root of 2 because it does not have a square root. That's how we reduced square roots. Cube roots are no different. If I have a cube root of 8, well, I don't want to think about perfect squares. I want to think about perfect cubes. So I say, well, 2 cubed is equal to 8. Oh, it is a perfect cube. So the cube root of 8 is 2. If I have something like the cube root of 27, okay, well, 2 cubed is 8. 8 doesn't go into 27. 3 cubed, let's see, 3 times 3 is 9, times 3 again is 27. Oh, it is a perfect cube. So the cube root of 27 is 3. What number cubed equals 27? It's 3. We can reduce them. If I have the cube root of 16, cube root of 16. So I look at my list of cubes. Well, 2 cubed is 8, and 3 cubed is 27. That's too big. So it's not a perfect cube. But I do notice that one of the perfect cubes, 8, does divide 16. It's 8 times 2. So I can break it apart and take the cube roots of those individually. The cube root of 8 is not 8, it is 2. And then this just stays the cube root of 2. Please notice that every time I have to write this 3, this index is important. If that index isn't there, it's a square root. This is square root of 8. This is cube root of 8. If that 3 is not there, that's a very different answer. You know, this one was 2 squared roots of 2. This one was just 2. That 3 has to be there. You want to be very careful and make sure you don't write it big. That is different than that. You have to be very careful with your placement. But these are all the different roots and the radicals. So the radical sign is all of the roots, not just the square root. As long as you know what the index is, you know which power you're doing the opposite of, and that is how we deal with the radicals. Now, the other thing we mentioned that we were going to be dealing with this lesson was rational exponents. So let's talk about the word rational again. We've seen that word before, rational numbers. A rational number, if you remember, comes from the word ratio, which is just another way of so a rational is just another word for a fraction. Okay, because ratio, fraction. So when we say rational exponents, what that means is that we are talking about there being a fraction in the exponent. So for example, if I have something like 4 to the 1/2 power. Now we are used to exponents. We've done exponents before. We know that that is some form of repeated multiplication. We know all our laws of exponents, the things that we can do with exponents and things that we can't do with exponents. But what does it mean if the exponent is a fraction? Or a decimal for that case, because don't forget, 1/2 is also 0.5 as a decimal. So that would be the same idea there. Those would be the same thing. So 4 to the 1/2 power or 4 to the 0.5 power is what we're talking about. You know, what does that mean if the exponent isn't just an integer, if it's a fraction? And it's a very interesting thing to think about. When we take a fraction exponent, we are actually dealing with roots. If we think about our laws of exponents, we can multiply exponents. You know, if you take a power to a power, you multiply the exponents. And when we multiply by fractions, that tends to divide things and break them up. We're dealing with roots. We're undoing exponents. So what you want to realize is in the fraction exponent, the fraction is telling us something. There's two parts to it. There's a numerator and there is a denominator. The numerator is just giving you an exponent. It's the number on top. It is an exponent. But the number here in the bottom is actually an index. And if you remember from our vocabulary on the page before, the index is the number that goes on that little shelf in the radical. So it's telling us which root we are dealing with. It's kind of our root. I've often heard it described as a flower. You know, the top number is the flower. It's flower power. Flower power. So the number on top is the power. It's the exponent. But then underneath the flower, you know, underneath the ground here, you have your roots. So, you know, underneath that fraction bar, top is the flower power, it's the power, and underneath the ground down here is the root. It tells you which root it is. So if our index is 2, That's a 2 root. Now we always said you don't have to write the 2. When the number is not there, it's an understood 2. But that would be a square root. So 4 to the 1/2 power is the same thing as the square root of 4, which we know is 2. You can have other powers. I could have 8, or any number, to the 1/3 power. Well, again, top number is my power, so it's 8 to the 1st power. The bottom number is my root, so that would be my index, my radical. So this is a cube root. The cube root of 8 is 2. They're not all just ones. We could have something like 27 to the 2/3 power. All right, so things that we want to think about when we have this extra number here. If this is 27 to the 2/3 power, it is a 3rd root, because that's the root. It's underneath, it's in the ground. So it's the cube root of 27, but it's not a 1 up top. So we're actually taking this to a power of 2. The cube root of 27 is 3, but then I've got 3 squared, which is 9. So this is my power, and this is my root. So we've got a power and a root. So I took the root, and then I took it to the 2nd power. You can go back and forth. I can write any radical as a fraction exponent. So let's say I have the 5th root of x cubed. All right, the 5th root of x cubed. Well, if I want to write that as a fraction exponent, whatever is inside the radical, what's inside the radical is our base. The radicand is our base. Our power goes on top, root goes on the bottom. So this would be x to the 3/5. And it can be written this way. Another way we could also write it would be the 5th root of x to the 3rd power. Those would be the same thing. As far as order of operations go, these are both considered to be exponents. So they kind of fall into the same level of order of operations. So these are actually interchangeable. They would be the same thing. So the order that we do them in does not matter. And so this, has a lot of things to write. So you can see why mathematicians were drawn to this idea of a fraction exponent, because this is a lot more concise. It's a lot more compact. It has all that information in one little fraction, because it's got my power, it's got my root. I didn't even have to draw a radical sign. That really saves me, a lot of writing. If I have something like 8x to the 2/3 power, here we also want to remember some things about our laws of exponents. The only thing that is being taken to the 2/3 power in this problem is the x. And so you don't want to have that 8 tagging along with the x. That 8 is just minding its own business. It is being 8. 8 is not being taken to the 2/3 power. So it's the x that has a cube root, because 3 is on the bottom, so it's the root. It's the x that is being squared, because it's got that power of 2. This is what has the fraction exponent. The 8, it's just there, minding its own business up front. So it needs to stay there, minding its own business up front. You don't want to lose it, but you're not going to take the cube root of it, and you're not going to square it, because x is the only thing that is being taken to the 2/3 power. You can go back and forth between fraction exponents and radicals. And one of the reasons that this is useful is that when we have radicals, we're really restricted to the math that we can do with the radicals. If radicals aren't the same, we can't add and subtract them. We can't multiply them if they're not both square roots. But with exponents, we have a lot more freedom. Remember, with our laws of exponents, if we multiply like bases, we can add the exponents. If we divide like bases, we can subtract the exponents. If we take a power to a power, we can multiply the exponents. And just because the exponent is a fraction doesn't change those rules. If I have x to the 1/4 times x to the 2/3, I can do that because my law of exponents says that if I multiply like bases, I add the exponents. So I would just have to do whatever 1/4 plus 2/3 is. Don't forget, they're just fractions, but that doesn't mean we can't add them. When you add, you get a common denominator, or if you have a calculator, you just type it in your calculator. But our common denominator would be 12. This would be 3/12. And then multiply this times 4, this would be 8/12. So 3/12 plus 8/12 would be 11/12. So this is x to the 11/12 power. That's how we just, none of our laws of exponents change. If I have a negative exponent, it doesn't matter if it's a fraction exponent or not, it's still going to move it down to the bottom of the fraction. Just because the exponent is a fraction does not change the laws of exponents.